Welcome back to Streamberg Space Stories. If you're new here, this is a place for long, quiet journeys through the science and mystery of space. No rush, no noise, just you, the dark, and a story worth thinking about. If that sounds like something you'd enjoy, consider subscribing. It really does help others find their way here too. Tonight, we're not going far. Not to a distant star or a hidden ocean beneath the ice of a frozen moon. Tonight, we're going somewhere familiar. Somewhere you have looked at 1,000 times without thinking about it. Somewhere that hangs in the sky most nights, so constant and so ordinary that it barely registers as extraordinary anymore. But it is extraordinary. And after more than half a century of absence, we're finally going back. Before you listen further, take a moment to settle in. Adjust your pillow if you need to. Let the day fall away. This is a story that stretches across decades, from the dusty footprints of the last astronaut to leave the lunar surface in 1972 to the crew that, as this recording was made, was preparing to fly around the moon for the first time in 54 years. It is a story about why we left, why we stayed away for so long, and why the return is not a repetition, but a beginning. Imagine for a moment that you're standing on the moon, not in a simulator, not in a photograph, actually standing there in a spacesuit on the surface. The ground beneath your boots is grey, not the grey of concrete or ash, but a softer, finer grey, the colour of charcoal mixed with powdered glass. It clings to everything. It gets into the joints of your gloves, the seals of your helmet, the threads of the fabric on your legs. This dust has been sitting undisturbed for billions of years, pulverized by micrometeorites and hardened by radiation, and it is so fine that it behaves almost like a fluid. When you step, your boot sinks a centimetre or two, and the print it leaves behind will remain for millions of years, because there is no wind to erase it, no rain to wash it away. Nothing moves here, nothing changes, nothing has changed for a very, very long time. The sky above you is black, not the deep blue black of Earth, but absolute, total black. There is no gradient, no fading at the horizon. The surface ends and the void begins, and if you look away from the bright ground, if your eyes adjust, you begin to see them. Stars, more than you've ever seen, unblinking, perfectly still. And there, hanging above the horizon, is Earth, blue and white and impossibly distant, larger than you expect, yet somehow feeling small. Every person you've ever known, every city, every ocean, every forest, every war and every love song and every argument about what to have for dinner, all of it fits behind your thumb. You're 240,000 miles from home, standing in the most complete silence that exists, on a world that has no sound at all. 12 human beings have stood where you are standing. All of them were American. All of them were men. All of them went between 1969 and 1972. And then, for reasons that had nothing to do with the moon and everything to do with the Earth, we stopped going. We packed up. We came home. And for 54 years, no human being returned. Until now. The Apollo program remains the single most ambitious thing our species has ever done. Between 1968 and 1972, NASA sent 9 crews to the moon, and 6 of them landed on the surface. They did this using technology that, by modern standards, is almost unbelievably primitive. The onboard computer in the Apollo command module had roughly 64 kilobytes of memory, and operated at a speed of about 1 megahertz. A modern smartphone is millions of times more powerful. The Saturn V rocket that carried them there was the largest and most powerful rocket ever successfully flown, a machine 363 feet tall, burning 5 engines that together produced 7.5 million pounds of thrust. It was built by hand, without computer-aided design, by a workforce of more than 300,000 people spread across 20,000 companies, and it worked. On July 20th, 1969, Neil Armstrong and Buzz Aldrin became the first human beings to set foot on another world. The landing was not graceful. Armstrong had to take manual control of the lunar module Eagle in the final minutes, flying past a boulder field that the onboard computer had targeted, searching for a flat spot to set down while the fuel gauge dropped toward empty. Mission control, 240,000 miles away, went quiet. The only voice on the radio was Aldrin's calling out altitude and descent rate. 60 seconds of fuel remaining. 30 seconds. Contact light. The Eagle had landed with roughly 25 seconds of fuel to spare. Armstrong's heart rate, which had been resting around 60 beats per minute, peaked at over 150 during the descent. They spent 2.5 hours on the surface. They collected rocks. They planted a flag. They left a plaque that read, "Here men from the planet Earth first set foot upon the moon. We came in peace for all mankind." They took photographs that would become the most reproduced images in human history. And then they climbed back into the lunar module, fired the ascent engine, and returned to Michael Collins, who had been orbiting above in the command module Columbia, alone, the most isolated human being who had ever lived, out of radio contact with Earth for 48 minutes of every orbit as he passed behind the far side of the moon. 5 more landings followed, each one more ambitious than the last. Apollo 12 demonstrated pinpoint landing, setting down within walking distance of the Surveyor 3 probe that had landed 2 years earlier. Apollo 14 saw Alan Shepard hit golf balls across the regolith. Apollo 15, 16 and 17 carried a lunar rover, a small electric car that allowed the astronauts to cover miles of terrain, reaching craters and mountain slopes that would have been impossibly far on foot. The later missions stayed longer, collected more, and conducted more sophisticated experiments. Apollo 17, the final mission, spent 3 days on the surface. Its crew, Eugene Cernan and Harrison Schmitt, who was the only professional geologist ever to visit the moon, collected over 240 pounds of samples, drove more than 20 miles across the Taurus-Littrow Valley, and deployed instruments that continued transmitting data back to Earth for years after they left. On December 14, 1972, Cernan climbed the ladder of the Lunar Module Challenger for the last time. He paused at the top, looked back at the surface and said, "We leave as we came, and God willing as we shall return, with peace and hope for all mankind." Then he sealed the hatch. The ascent engine fired, and no human being has set foot on the moon since. That was more than half a century ago. In the years since, we have sent robots to Mars, launched telescopes that can see the first galaxies, landed a probe on a comet, and built a space station that has been continuously occupied for more than 25 years. But we have not gone back to the moon. The question is why? Before we answer that, it is worth noting what we did bring back and how much it taught us. The Apollo missions returned 842 pounds of lunar samples, rocks and soil from 6 different landing sites. Those samples have been studied continuously for more than 50 years, and they are still producing discoveries. It was Apollo samples that confirmed the leading theory of the moon's origin, the giant impact hypothesis, which holds that a Mars-sized body called Theia collided with the young Earth roughly 4.5 billion years ago, and the debris from that collision coalesced to form the moon. It was Apollo samples that revealed the moon once had a global magma ocean, a sea of molten rock that covered the entire surface, and it was Apollo samples that showed the interior of the moon is far drier than the Earth's, though not entirely dry, a puzzle that remains the subject of active research. NASA was careful to preserve some of those samples for the future, sealing containers of lunar material in pristine conditions, waiting for a time when better instruments would be available to study them. In recent years, those sealed samples have been opened and analysed with technologies that did not exist in the 1970s, including mass spectrometry and electron microscopy, far more sensitive than anything available to the original Apollo scientists. The moon has been teaching us things for 50 years, and it is not finished. The answer is not simple, but it is honest. We stopped because the reason we went was not science, it was politics. The Apollo program was born out of the Cold War, out of the shock of the Soviet Union launching Sputnik in 1957 and putting Yuri Gagarin into orbit in 1961. President Kennedy's famous 1961 speech, in which he committed the nation to landing a man on the moon before the end of the decade, was not primarily a scientific statement. It was a geopolitical one. The moon was a finish line in a race between two superpowers, and once the race was won, the urgency evaporated. By the time Apollo 17 flew in 1972, public interest had already waned. The launches no longer dominated the news. The Vietnam War, the Watergate scandal, and a struggling economy consumed the nation's attention and its budget. NASA's funding, which had peaked at roughly 4.5% of the federal budget during the mid-1960s, began to decline. Within a few years, it had fallen to under 1%, where it has remained ever since. The Saturn V production line was shut down. The remaining rockets were sent to museums. The infrastructure that had carried 12 men to the moon was dismantled, and the institutional knowledge, the practical, hands-on understanding of how to build and fly those machines, began to fade as the engineers who built them retired and eventually died. This is a detail that is often overlooked, and it is worth sitting with for a moment. Going to the moon is not like riding a bicycle. You do not simply remember how to do it. The Saturn V was never fully documented in the way that modern engineering projects are. Much of the manufacturing was done using craft skills, learned on the job, passed from one technician to another through years of practice and apprenticeship. The composition of certain adhesives, the precise techniques for welding certain fuel lines, the tolerances achieved by hand-fitting components, these things existed in the hands and the heads of the people who did the work. When those people left, the knowledge left with them. By the 1980s, even if NASA had wanted to fly to the moon again using the same hardware, it could not have done so without essentially reinventing the process from scratch. The capability had not been destroyed, it had evaporated. Like a language that dies when the last person who speaks it dies. The words are in the dictionary, but the living knowledge of how to use them is gone. There is a quiet lesson in this. Capability is not permanent. It must be maintained, practiced, funded, and passed on. The greatest technological achievement of the 20th century was allowed to lapse not because it was superseded by something better, but because no one was willing to pay the cost of keeping it alive. The rockets were retired, the factories were repurposed, the engineers took other jobs, and the moon, having been touched by human hands, went back to being what it had been for 4.5 billion years, unreachable. For decades after Apollo, the moon existed in a strange limbo. It was the most famous destination in human history, but no one was going there. NASA's focus shifted to the Space Shuttle, a reusable winged spacecraft designed to operate in low Earth orbit, carrying satellites, servicing Hubble, and building the International Space Station. The shuttle flew 135 missions over 30 years. It was an extraordinary machine, but it was designed for a fundamentally different purpose than Apollo. It could not leave low Earth orbit. It could not reach the moon. It was a truck for near space, not an explorer of other worlds. The International Space Station, which has been continuously occupied since November 2000, taught us an enormous amount about living in space. It demonstrated that human beings can survive in microgravity for months, even more than a year, though not without cost. It proved that international cooperation in space is possible, with modules built by the United States, Russia, Europe, Japan, and Canada functioning as a single integrated laboratory. But the station orbits at an altitude of roughly 250 miles. The Moon is 1,000 times farther away. The station is a place to work in space. The Moon is a place to work on another world. The distinction matters. There were plans to go back. Several presidents announced return to the Moon initiatives, and each one followed the same arc: ambition, funding, delay, cancellation. In 1989, George H.W. Bush proposed the Space Exploration Initiative, which included a return to the Moon and an eventual mission to Mars. The estimated cost was $500 billion. Congress rejected it. In 2004, George W. Bush announced the Constellation program, which aimed to return astronauts to the Moon by 2020 using a new generation of rockets and spacecraft. The Ares 1 and Ares 5 rockets were designed, prototypes were built, and then the program was cancelled by the Obama administration in 2010. The Orion crew capsule, however, survived. It was too far along and too costly to abandon. It was carried forward into what would, years later, become the Artemis program. In 2017, the Trump administration signed Space Policy Directive 1, formally directing NASA to return to the Moon as a stepping stone to Mars. The program was named Artemis, after Apollo's twin sister in Greek mythology, the goddess of the Moon. Each of these false starts consumed years and billions of dollars. Each left behind fragments of hardware, pools of expertise, and a deep institutional frustration. The pattern became so familiar that it acquired a kind of cynicism within the space community. Announce a bold program, fund it for a few years, cancel it when the next president arrives, start over. The Moon remained where it had always been, 240,000 miles away, close enough to see with your eyes, and yet, for half a century, unreachable. So what changed? Why, after all these false starts, is the return finally happening? The answer involves science, economics, technology, and a shifting global landscape that has made the Moon, once again, a place worth fighting for. The scientific case is stronger than it has ever been. In the decades since Apollo, robotic missions have revealed the Moon to be far more interesting than the 6 landing sites suggested. In 2009, NASA's LCROSS mission deliberately crashed a spent rocket stage into a permanently shadowed crater near the Moon's south pole and detected water ice in the debris plume. Subsequent missions confirm that billions of tons of water ice may be trapped in these craters, regions that have not seen sunlight in billions of years, where temperatures drop below -300 degrees Fahrenheit. Water on the Moon is not merely a curiosity, it is a resource. Water can be drunk. It can be split into hydrogen and oxygen, providing breathable air and rocket fuel. A sustainable human presence on the Moon depends on being able to use what is already there, rather than carrying everything from Earth. This principle, called in situ resource utilization, is the foundation of every serious plan for long-duration lunar habitation. The technological case has also matured. SpaceX has fundamentally changed the economics of spaceflight. The cost of launching a kilogram to orbit has fallen by roughly a factor of 10 since the Space Shuttle era, and continues to fall. The Falcon Heavy, the rocket that launched Europa Clipper and the Artemis II crew, is a fraction of the cost of the SLS. Meanwhile, SpaceX's Starship, the largest and most powerful rocket ever built, is designed to be fully reusable and capable of carrying more than 100 tons to the Moon's surface. Blue Origin is developing its Blue Moon lander. Axiom Space is building the spacesuits. The Artemis program is, by design, a partnership between NASA and the private sector, structured to distribute cost and risk in a way that Apollo never attempted. And then there is the geopolitical dimension, which is perhaps the factor that has done most to accelerate the timeline. China has conducted a series of increasingly ambitious robotic lunar missions. Chang'e 4 in 2019 became the first spacecraft to land on the far side of the Moon. Chang'e 5 in 2020 returned samples from the near side, the first lunar sample returned since the Soviet Lunar 24 mission in 1976. Chang'e 6 in 2024 returned samples from the far side of the Moon, a world first that required a relay satellite in orbit to maintain communications. China has announced plans to land taikonauts on the Moon by 2030 and to establish the International Lunar Research Station, a permanent base on the South Pole, in partnership with Russia and other nations. The station's first phase envisions robotic construction beginning around 2030, with crewed missions to follow. India landed its Chandrayaan-3 rover near the South Pole in 2023, becoming the fourth nation to achieve a soft landing on the Moon. Japan landed its SLIM spacecraft in early 2024. South Korea, the European Space Agency, Israel, and several private companies are all pursuing or planning lunar missions. The Moon, for the first time since the 1960s, is contested territory. Not in a military sense, but in a strategic one. The nations and organizations that establish a presence on the Moon first will shape the rules, the norms, and the infrastructure of lunar activity for decades to come. The Artemis Accords, signed by more than 60 nations as of 2026, represent an American-led attempt to establish a framework of peaceful cooperation before the frontier becomes crowded. But not all spacefaring nations have signed. China and Russia have not. The Artemis program is not Apollo repeated. It is something different and in many ways more ambitious. Apollo was a sprint. 12 men, 6 landings, 3 years, done. Artemis is designed to be permanent. The goal is not merely to visit the Moon, but to stay there, to build infrastructure, to learn how to live and work on another world, and to use the Moon as a proving ground for the technologies and the skills that will one day carry humans to Mars. The program is built around several key elements. The Space Launch System, or SLS, is a heavy-lift rocket derived from space shuttle components designed to send the Orion crew capsule and its astronauts beyond low Earth orbit. Orion, built by Lockheed Martin with a European service module provided by the European Space Agency, is the crew vehicle. It carries up to 4 astronauts, provides life support for missions lasting up to 3 weeks, and is designed to withstand the punishing re-entry speeds of a return from the Moon, roughly 25,000 miles per hour. The Human Landing System, the vehicle that will actually carry astronauts from lunar orbit to the surface, is being developed commercially. SpaceX's Starship HLS, a variant of the massive Starship rocket, is designed to land vertically on the Moon and provide a habitat for crew during their surface stay. Blue Origin's Blue Moon lander is the second option under contract. The spacesuits that astronauts will wear on the lunar surface are being designed by Axiom Space in collaboration with the Italian fashion house Prada, producing suits that are more flexible, more protective, and more functional than anything worn during Apollo. The selection of which lander will fly first depends on the results of Artemis III, now scheduled for mid-2027, which will test one or both landers in low Earth orbit. If those tests succeed, Artemis IV, targeted for early 2028, will be the mission that returns humans to the lunar surface for the first time since 1972. The surface mission will last roughly a week, with subsequent missions planned approximately once per year, each one staying longer, and, building on what came before, the landing site will not be in the equatorial regions explored by Apollo. It will be near the Moon's south pole, where the permanently shadowed craters hold water ice, and where the conditions are more challenging, the terrain rougher, the temperatures more extreme, but the scientific and resource potential far greater. The crew will spend roughly a week on the surface, conducting experiments, collecting samples, and testing technologies that are explicitly designed with Mars in mind. Every system proven on the Moon is a system that can be adapted for a mission to the Red Planet. NASA calls this approach Mars Forward, meaning that every piece of lunar hardware, every operational procedure, every lesson learned is part of a longer arc that ends not on the Moon but on Mars. As this recording was made in the spring of 2026, the first crewed step of that journey was underway. Artemis II, launched on a Space Launch System rocket from Kennedy Space Center in Florida, is carrying 4 astronauts on an approximately 10-day mission around the Moon and back to Earth. The crew consists of Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen. Glover is the first black astronaut to travel beyond low Earth orbit. Koch is the first woman. Hansen, a Canadian Space Agency astronaut, is the first non-American to fly to the Moon's vicinity. These are not footnotes. They're a statement about who this program is for. The mission profile is comparable to Apollo 8 in 1968, the first crewed mission to fly around the Moon, and in some ways it is even more ambitious. The crew will orbit Earth twice while testing Orion's systems, then fire the upper stage engine to send the spacecraft on a free return trajectory around the Moon. They will pass roughly 4,700 miles beyond the far side, farther from Earth than any human being has ever been, surpassing the record set by the crew of Apollo 13 in 1970. For several minutes during the far side flyby, parts of the lunar surface that were never seen up close during Apollo will pass beneath them. They will not enter lunar orbit. They will not land. But they will test Orion's life support systems, navigation, and deep space communication links with a crew aboard for the first time. They will also carry a biological experiment called Avatar, which mimics the response of human tissue to radiation, providing data that will be critical for longer missions. The entire flight will last approximately 10 days, from launch to splashdown in the Pacific Ocean off the coast of San Diego. There is something quietly moving about this mission. 54 years have passed since Apollo 17. In that time, the astronauts who walked on the Moon have grown old. Several have died. Neil Armstrong died in 2012. Buzz Aldrin, who set foot on the Moon at the age of 39, is now 96. Eugene Cernan, the last man to stand on the lunar surface, died in 2017 without seeing anyone follow in his footsteps. Harrison Schmitt, the youngest moonwalker, is 90. An entire generation was born, grew up, raised children of their own, and is now approaching retirement without ever seeing a human being leave low Earth orbit. Artemis II does not land on the Moon, but it reopens a door that has been closed for longer than most people alive today have been alive, and for the men who walked on the Moon and lived long enough to see this day, it is a vindication. A confirmation that what they did was not an ending, but the first chapter of a longer story. The Moon is not merely a destination. It is a laboratory, a time capsule, and a testbed, and it offers something that no other world in the solar system can: proximity. As a laboratory, the Moon provides an environment that cannot be replicated on Earth. Its surface is exposed to the full spectrum of cosmic radiation, to the solar wind, to micrometeorites, and to temperature swings that range from 260 degrees Fahrenheit in direct sunlight to -280 in shadow. Material science, radiation biology, astronomical observation, and geological research can all be conducted on the Moon in ways that are impossible anywhere else. The far side of the Moon, permanently shielded from Earth's radio noise, is the quietest place in the inner solar system, and astronomers have long dreamed of building a radio telescope there, one that could detect signals too faint to be heard from Earth. As a time capsule, the Moon preserves a record of the solar system's history that has been erased everywhere else. The Earth's surface is constantly recycled by plate tectonics, weathered by wind and water, reshaped by life. Mars has lost most of its atmosphere and surface water. Venus is shrouded in cloud and resurfaced by volcanic activity. But the Moon has none of these processes. It has no plate tectonics, no atmosphere, no water, no life. Its surface is a geological archive stretching back 4.5 billion years, preserving impact craters, lava flows, and layers of regolith that record not only the Moon's own history, but the history of the Sun, the inner solar system, and the bombardment that shaped the early Earth. The Late Heavy Bombardment, a hypothetical period of intense asteroid impacts roughly 4 billion years ago, may have delivered water and organic molecules to the young Earth, seeding the conditions that eventually led to life. Evidence for or against this event is best preserved not on Earth, where it has been erased by geological activity, but on the Moon, where the craters from that era are still intact, waiting to be studied. And as a testbed, the Moon is the only place where we can practice living on another world without the consequence of irreversibility. Mars is a 6-month journey each way. If something goes wrong on Mars, there is no rescue, no abort, no coming home early. The Moon is 3 days away. Communication with Earth is nearly instantaneous, just a 1 1/3 second delay each way. In an emergency, the crew can return. This makes the Moon the ideal place to fail safely, to discover the flaws in a habitat design, a power system, a spacesuit, or a medical protocol, before those flaws become fatal on Mars. The radiation environment is particularly important. The Moon, like Mars, has no global magnetic field and almost no atmosphere. Its surface is exposed to the same galactic cosmic rays and solar particle events that a Mars crew would face. NASA's Kilopower nuclear fission reactor, designed to provide reliable power during the long lunar nights and eventually on Mars, will be tested on the lunar surface. The lunar surface habitat, currently in development, will serve as the primary testbed for life support hardware in partial gravity. Water recycling systems, air scrubbers, medical equipment, exercise protocols, all of these will be validated on the Moon before they are trusted to keep people alive on a planet where help is 7 months away. Every technology that works on the Moon has a reasonable chance of working on Mars. Every technology that fails on the Moon is a technology that would have failed on Mars with far worse consequences. That margin of safety is worth everything. The Artemis landing site near the Moon's south pole is a fundamentally different environment from the equatorial regions explored by Apollo. The Apollo astronauts worked in flat, sunlit plains, under a sky where the sun rose and set in a 14-day cycle. The South Pole is a landscape of extremes. Long, jagged shadows stretch across cratered terrain. Some ridges and peaks are bathed in near-constant sunlight, while the floors of nearby craters have not seen a single ray of light in billions of years. These permanently shadowed regions are among the coldest places in the solar system. Temperatures in the deepest craters drop below -400 degrees Fahrenheit, colder than the surface of Pluto. And it is in these craters that water ice has been detected, preserved by the cold and the darkness, possibly delivered by comets and asteroids over billions of years. The amount is uncertain, but some estimates suggest billions of tons. If this ice can be extracted and processed, it would transform the economics of lunar exploration. Water is heavy and expensive to launch from Earth. Finding it on the Moon means you do not have to bring it, and water is not just for drinking. Electrolysis splits it into hydrogen and oxygen. Oxygen is breathable air. Hydrogen and oxygen together are rocket propellant. A lunar base with access to water ice could, in principle, refuel spacecraft, produce its own air, and sustain a crew indefinitely without resupply from Earth. The Moon could become a filling station, a waypoint where spacecraft on their way to Mars or the outer planets stop to refuel using propellant manufactured from lunar ice. This idea, once science fiction, is now a serious engineering objective. There are other resources too. The regolith contains helium-3, a light isotope deposited on the Moon's surface by the solar wind over billions of years, theoretically valuable as fuel for nuclear fusion. More practically, the regolith itself can be used as building material. NASA and private companies have demonstrated 3D printing techniques using simulated lunar soil to create structural components, radiation shielding, and landing pads. The vision is a lunar economy that uses local materials for construction, local water for life support and fuel, and imports from Earth only the things that cannot be made on site: electronics, specialized equipment, and people. This is the vision that drives Artemis. Not a flag-planting visit, but a sustained presence, a base, a settlement, eventually. A place where people live and work, not for days, but for weeks, then months, then longer. The first steps will be modest. A week on the surface, a few experiments, some samples collected, but each mission will stay longer, carry more, and build on what came before. By the early 2030s, if the program proceeds as planned, there could be a semi-permanent habitat near the South Pole, powered by nuclear fission, supplied by robotic cargo landers, and occupied by rotating crews who come and go on a regular schedule. The challenges of sustaining a human presence on the Moon are not trivial. Lunar dust, the fine, abrasive regolith that covers the surface, is one of the most underestimated hazards. During Apollo, astronauts reported that the dust got into everything. It clogged seals, scratched visors, and irritated lungs when it was tracked back inside the lunar module. The dust is electrostatically charged, which makes it cling to surfaces like a magnet. It is rich in tiny glass particles, formed by micrometeorite impacts, which makes it sharp and abrasive. And it contains perchlorates, chemicals that are toxic to human biology when inhaled or ingested. Managing lunar dust over weeks or months, rather than the days that Apollo spent on the surface, will require engineering solutions that do not yet fully exist. Airlocks, dust mitigation systems, suit maintenance protocols, all of these will need to be developed, tested, and proven. This is precisely the kind of problem that can only be solved by going there and staying long enough to encounter it. There is one more reason we're going back to the Moon, and it is perhaps the most important, though it is the hardest to quantify. It is the effect that exploration has on the people who do it and the people who watch. The Apollo program did not merely land astronauts on the Moon. It produced the most famous photograph in history. On December 24, 1968, astronaut William Anders, aboard Apollo 8 during humanity's first flight around the Moon, looked out the window and saw something that no human eye had ever seen: the Earth rising above the lunar horizon. He grabbed a camera and took a photograph. The image, known as Earthrise, showed our planet as a small, fragile blue and white sphere suspended in the absolute blackness of space, rising above a barren, grey, lifeless foreground. It was not planned. It was not on the mission checklist. It was a moment of spontaneous wonder, captured on Kodak film, that changed the way an entire species thought about its home. The photograph is widely credited with helping to launch the modern environmental movement. The first Earth Day was held 2 years later, in 1970. The Clean Air Act, the Clean Water Act, the Endangered Species Act, the creation of the Environmental Protection Agency, all of these followed within a few years of that single photograph taken from the vicinity of the moon. For the first time, humanity could see itself as the inhabitants of a single, finite, borderless world, a blue marble floating in darkness, with no visible lines between nations, no evidence of the divisions that consume so much of our energy on the ground. The most important thing Apollo brought back from the moon was not rocks, it was perspective. Artemis has the potential to produce its own version of that moment. The cameras will be better, the footage will stream live in high definition, the crew will be more diverse than any that has flown before, and the audience will be global in a way that Apollo's could not have been, connected by smartphones and social media that did not exist in 1969. When a woman sets foot on the moon for the first time, when a black astronaut looks back at the Earth from the lunar surface, when a Canadian plants footprints in the regolith alongside American ones, these will not just be milestones for the space program, they will be milestones for the species. Moments that children will remember, that teachers will point to, that will sit in the collective memory the way Apollo 11 does for an earlier generation, and they will be watched, live by billions. The moon is patient. It has been waiting for 54 years. It has been waiting in truth for 4.5 billion years, since a Mars-sized body collided with the young Earth and the debris coalesced into a companion that has been circling us ever since. It was there when the first fish crawled onto land. It was there when the first humans looked up and wondered what it was. It was there when 12 men walked on its surface and came home. And it was there during all the decades when no one came back. It is still there. Tonight. Every night. 250,000 miles away. Close enough that you can see its craters with a pair of binoculars, close enough that light reaches it in just over a second, close enough that a spacecraft can get there in 3 days, the closest world to ours, the first step beyond home. And we are taking that step again, not because a rival demands it, though rivals sharpen the urgency, not merely because the science justifies it, though it does, but because there is something in us, something stubborn and impractical and essential, that refuses to look at the sky and not wonder what it would be like to go. We went to the moon in 1969 because we were afraid of what would happen if we didn't. We are going back now because we have learned what we lost by stopping. The moon is not the end. It is the beginning. The technologies we prove there will fly to Mars. The lessons we learn there will keep astronauts alive on a planet 7 months away. The base we build there will be the first permanent human settlement on another world, not the last. And the generation that grows up watching Artemis land on the South Pole will be the generation that someday boards a spacecraft for Mars. They will carry with them everything we have learned, on the moon, on the station, in the simulators and the test chambers and the sealed habitats in the Texas desert. They will carry the mistakes and the corrections and the quiet, unglamorous patience of people who spent decades solving problems so that others could go. Somewhere right now, as you listen to this, 4 astronauts are falling through the dark toward the moon. They are the first humans to leave low Earth orbit in more than half a century. They will not land. Not this time, but they are opening a door, and behind that door is a future that begins with footprints in the grey dust near the South Pole and ends, eventually, on the red soil of another planet, in a place we have not yet been and cannot yet imagine, but that we are, step by slow step, learning how to reach. Thank you for listening to Strindberg Space Stories. If this story gave you something to carry into the night, subscribing truly helps us keep making these, and I am grateful for every one of you who does. Take care of yourself, sleep well. Good night.